Okay, now this is your recent set of slide, out of which the very first thing that is causing you problem is this slide number 7. Yeah, and over here they have given you the general form of your population linear regression model. As far as the term linear is concerned, you can see that this linear thing represent that you are discussing a straight line regression model representing the best fit in the form of a straight line. Okay, so that is when you just try to figure out the best fit that is covering all the scattered plots on a 2D graph. Then the best fit is coming out in the form of a straight line. So such regression model is actually appearing in the form of a straight line, so that's why it's called a linear regression model. All right, so as far as the population linear regression model is concerned, it is a very time consuming thing. Like if I say that just determine all, just compile the data of all the Pakistani population and just figure out and just relate the heights of all Pakistanis and with respect to the size of their hands. Okay, this is a correlation question. So for that purpose, you have to take the survey of the whole country, and then you have to compile that whole big, large, gigantic data, and then you just make a correlation by plotting the scattered plot diagrams and then obtaining the regression model. So this is a very, very time consuming thing. So you need a very you need something very precise and a method through which you can obtain very, very close answers or very, very accurate answers in a short span of time. So how about if you just pick up a sample out of this whole population and you just get a scattered plot and you get a linear regression best fit line, and you just form a straight line equation on the format of y is equals to mx plus c. And with respect to that that equation of a straight line that you have obtained with the help of sample data, you are going to predict, or you are going to estimate the best possible answers of these parameters. Okay, you can see that this is the equation of your population. Okay, out of which this is your mx, and m is represented by the beta 1, and c is the y-intercept that is represented here by your beta naught. Okay, and epsilon is the random error, and I have just we have just discussed the concept of standard error of estimate when we were discussing the correlation. Okay, so you know well the what exactly the standard error was. It was actually the difference between your actual value and the predicted or estimated value. Okay, you also call actual value as the observed value, if you remember. You can recall that video whenever you get the time. So it was, the error is actually the difference between the estimated value and your actual value that you have obtained in the sample data. Okay, so actually the story was going on like this. Like if I just represent my actual value with just y, and I represent my observed predicted value with my y dash, the difference between these two values is taken as the standard error, and we just call it, in case of population data, we just represent it with the epsilon notation. This is called the epsilon. Okay, it's called the epsilon. Okay, it is a Greek notation. All right, so once this y is representing the actual answer, actual data value, so I can write my y as my y dash plus epsilon. Okay, this is the error. So I just shift this negative y dash over here, it becomes positive. This is the basic maths. So, and in the beginning, when we were doing the correlation discussion, over there I explained that this y dash is actually the y that you obtain through the best fit line, you obtain the equation of the line of best fit, and it was of this format: y is equals to mx plus c. Okay, so here if you were discussing your sample your population data, so over here the y-intercept is your b naught. Okay, and your m is taken as your beta 1. Okay, so once your y dash is expressed like this, once you substitute the value of your y dash over here, you are getting this equation. Okay, and as far as you can see, these small i's in the subscript, you can see these small i's in the subscript, these small i's, this I, this I, and this I. This is actually the value. This is representing every single value which is present in your data. Like if you talk about the first value, it is taken as x1. You substitute your x1 over here. The corresponding first random error between the between the y1 and y dash 1. Okay, that is your y. That is your first error. Epsilon 1. You just substitute over here. You were going to get your y1. Okay, it comes out to be something like this. Let me use here a box. Okay, it is going to be y1 equals to your it takes too much time in putting the symbols, so just forget about the box equation. Let us use a freehand. It doesn't consume time. So if you talk about your y1, the first y value, then it is going to be obtained by substituting the first independent variable value, that is your x1, and this epsilon 1 is the first random error that you obtain by subtracting your first actual value with the first estimated value. So that's how, no matter how many values you're having in your sample data, 1,000, 1 lakh, 1 million, so all this number is representing the position of that data values. Okay, so no need to get confused. This is a general form. So that's it.